Good evening, ladies and gentlemen, and welcome to Astronomy on Tap Atlanta. I am your host, Justin Robinson, and it is my pleasure to welcome somebody who will be returning to the Astronomy on Tap Atlanta stage. Please give a round of applause for Astro PhD candidate Colin Kane. Colin uses the biggest infrared telescope on planet Earth, owned by Georgia State University, the Center for High Angular Resolution Astronomy, or the CHARA array, to study the most nearby stars to us in the highest detail that anybody can. And he's going to use that knowledge and others to tell you what the true size scale is of the universe. So without further ado, please give one more round of applause for Colin.
All right. Thank you very much, Justin, for the very kind remarks. Yes, as Justin said, this is going to be my second time talking at this wonderful establishment. But this is going to be a lot different than my first talk. So a year and a half ago, I gave a talk about the life cycle of stars, and this is going to be way, way, way different. So the motivation behind this was a lot of these talks talk about the sizes of celestial objects and these large-scale objects, and we don't really have like a good context to visualize how big these objects actually are. So today I'm going to be talking about how big actually is space. And before we get started, I just want to let you guys know that this is going to be the most American talk that you see, if you've been coming to a lot of these, because what the F is a kilometer? We're not talking about it today. There's going to be 0 kilometers in this talk. All right, so now let's get started on the actual science. So first, I'm going to show you guys some images of the objects that are closest to us, and those will be the planets. And all of these images are going to be to scale. It's good. So first, we have the closest to the sun, and we're going to be going out as we go on. So first is going to be Mercury. This is going to be the closest planet to the sun and is the smallest of the planets. Next, we go out to our evil twin, Venus. It's the second furthest from the sun. It is also the hottest surface temperature of any planet in the solar system. Next is going to be a planet that I don't think I have to introduce to you guys. You can see why we call Venus Earth's twin. It's very, very close in size to the Earth, with the Earth just being slightly larger. Then is going to be the little red friend Mars. So Mars is about half the size of the Earth and is quite small when you compare it to the size of Venus and Earth. Mars is also the only planet to be fully inhabited by robots, which is very cool. All right. Next, we'll go out to the larger of these planets. So to fit the outer planets onto the screen, we're going to have to shrink down our terrestrial friends up to the top corner. And next, we're going to have the king planet named for the Roman king of the gods, Jupiter. So Jupiter these are also to scale. I just want to reiterate that. This is actually how large Jupiter is compared to the terrestrial planets. Next, we have my favorite planet, Saturn. And if you're looking at that, you might be thinking, have I had too many beers, or does that planet actually look like an oval? And it actually does look like an oval. So you'll see that the axis where the rings are is slightly wider than it is tall, and that is because Saturn is actually spinning so fast that it's actually oblate. So I think that's a pretty cool thing about Saturn, along with its rings. So the next one is going to be Uranus. It's pronounced Uranus. And that is all I have to say about Uranus. And then we have Neptune. Neptune is the second of what we call the ice giants. These planets are so far away from the sun that they're so cold, their atmosphere is made up of mostly ices, as compared to the gas giants planets, which are close enough where the ices don't typically form in their atmospheres as much as they do in the ice giants. All right. Now, the elephant in the room, what's the last thing in the solar system? And that is going to be the sun. Yes, the sun is to scale. I couldn't fit the sun on this slide while also still being able to see any of the terrestrial planets. And that's because the sun makes up 99.9% of all of the mass in the solar system. So almost all of the stuff that makes up our solar system is in the sun, and of the rest of it, Saturn or Jupiter makes up 71%. So of the 0.1%, 71% of it is in Jupiter, which just shows first how large Jupiter is, second how large the sun is, and how small we are in comparison. All right. Now let's focus in on the Earth. So 1.3 million Earths could fit inside the volume of the sun. And if we take a look at a little tiny portion of the sun in that white square right there and zoom out, we can see the surface of the sun looks like almost like the skin of a football, where it has like this textured pattern. Those granules is what they're called, are actually different convective cells in the sun, but they could be the size of Texas. So they look really, really small on the size of the sun, but they are actually enormous. These are giant things. So as Howie would say, outside bad, the sun is scary, the sun is a monster. But luckily the sun is pretty dang far away. So the sun is 1.4 billion football fields away, which is also 120,000 Texases. If you were to count all of the yards that the NFL quarterbacks have thrown this year, it is about 132,000 in the 25-26 regular season. Go Hawks. And that only makes up 0.088% of the distance to the sun. All right. So we should not be afraid of the sun anymore. It's pretty dang far. All right. Now let's go to our close friend, the moon. So this one I want you guys to answer along. So how many planets do you think could fit in the distance between the Earth and the moon? None of my lab students are here, right? All right, cool. Sure. 33% of a Jupiter. All right, that's a great answer. It's wrong, but it's great. All right, so we're going to walk through one by one. The first one you see Mercury. So the planets are scaled to the distance between the Earth and the moon in this slide. They're not actual. The Earth isn't actually that much bigger than Mercury. But so we could fit Mercury, Venus, Earth, and Mars pretty easily. Then it gets interesting when you get to the gas giants. So you can add Jupiter and Saturn, as well as both of the ice giants. So ding, 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 you win a prize. I don't have anything to give you. All of the planets can actually fit in between the distance between the Earth and the moon. A fun fact about the moon's distance is that it is 400 times, around about 400 times closer than the Earth is to the sun, but the sun happens to be about 400 times larger in physical size than the moon, so they end up being the same angular size in the sky. This means that when you look up in the sky, they take up the same amount of space, and that would be half a degree. 1 degree is if you stick your pinky out and you hold your arm at an arm's distance, your pinky is about 1 degree wide. So half of that is going to be the angular size of the sun and the moon. But what this allows is for total solar eclipses. So at perfect time of the orbit, the moon will pass right in front of the sun, and that we will be able to block the entirety of the light from the sun in a specific part of Earth. So if you ever see solar eclipses, know that it's just luck of the draw that our moon just so happened to be 400 times closer, but 400 times smaller than the sun, so they're the same size. All right. Now we're transition from their relative sizes of the planets to how far out they are. So we'll start with the sun again, and we'll go from closest to furthest. So we'll start with Mercury, which is 0.4 AUs. So AU stands for astronomical unit, and is just a fancy way of saying the distance between the Earth and the moon, or the Earth and the sun. Sorry, Earth and the sun, 1 AU. So 0.4 is going to be the distance to Mercury. Venus is going to be 0.7, which means that Venus is 70% the distance from the Earth to the sun, from the sun. Really weird way to put that. And then the Earth obviously is going to be 1, as it's defined. And Mars is going to be 50% further at 1.5 AU. So then we have a little bit of a gap. There's the asteroid belt, which resides between 2 and 3 AUs from the sun. And then we have Jupiter. So Jupiter is going to be 5 AUs from the sun. Saturn is going to be right about 10. Uranus is going to be at 20. And Neptune is going to be at 30. So an easy way to remember the distances to the outer planets, if you ever wanted to know that, is that it goes 5, 10, 20, 30, and Pluto is right about 40. So if you ever were held at gunpoint and somebody asked you to list the distance to the outer planets, now you know. You're welcome, I saved your life. All right, now let's talk about some of our closest neighbors that are not in our solar system. And this would be the star Proxima Centauri. So Proxima Centauri is 4.3 light years from our sun. It is at very conveniently named Proxima Centauri because it's closest in proximity to us. But it's only closest to us at certain parts of its orbit because it's actually part of a triple system. So Proxima Centauri is part of a system of 3 different stars. These are going to be called Rigel, Kentaurus, Ptolemon, and Proxima Centauri. Rigel, Kentaurus, and Ptolemon are going to be G and K stars, so they're going to be similar to that of the sun. And Proxima Centauri is a little M dwarf. So what happens is that the 2 sun-like stars orbit each other closer in, with Proxima orbiting farther out between the 2 of them. And so it just so happens that at this point in time, when I'm giving this presentation, that Proxima Centauri is closest to the sun, but at later parts of its orbit, that is not the case. I don't know the orbital period of Proxima Centauri. Yeah, so in a few hundred to 1,000 years, if you guys come back here for another talk, that might be different, but as of right now, it is Proxima Centauri. But you might be asking yourself, what the heck even is a light year? Before I get to this. Beer break. Yeah. All right. No, it's not Buzz, unfortunately. It's actually the, yeah, you like that one? It's the distance that light travels in 1 year, which is 5.9 trillion miles, which is 2.1 billion times the distance from New York to LA. This means that light would have to travel at over 186,000 miles per second, or just about how fast people drive on 285. And it means that light takes 8 minutes and 20 seconds from when it leaves the surface of the sun to when it hits Earth. And the speed of light is the universal speed limit. So that actually is the speed of light in miles per hour. The speed limits are not like American speed limit signs where it's like it's a suggestion. Like nothing can move faster than the speed of light. So if you're looking at something that is X amount of light years away, you are seeing the light that left the surface of that object that many years previous. So I will give the example of the star Vega. For no particular reason. I definitely don't talk about it in a paper that I wrote that should be coming out sometime later this year. All right, so Vega is an A-type star, and it is actually the 5th brightest star in the night sky. So if you guys want to stay up till about 1 or 2 a.m., Vega will be up in the night sky tonight, but yeah, you guys have to stay up real late. Three Taverns won't stay open that late for us to observe it. But it is 25 light years away. So if somebody was living on a planet that was orbiting Vega and they looked at the Earth, they might see us watching Shrek for the first time. Or more realistically, if they had some sort of radio transmitter and pointed it right at the Earth and they were able to pick up our FM radio, they might hear something like this. All right. Hope you guys enjoyed the little Creed break. All right. So I mentioned the different types of stars, but you guys may or may not know exactly what I was talking about there. So here is a diagram of the different spectral types of stars. Essentially, this is a way that astronomers use to classify stars by their temperature and the mass of the star. So M stars are going to be these ones all the way down at the end. We don't care about those. And then O stars are going to be the most massive, hottest stars over here at the end. And we are here. The sun is going to be a G2 star, which is similar to that of Rigel, Kentaurus, and Ptolemy, which was a K star. Rigel, Kentaurus is a G star. So some of the closest stars to us just so happen to be similar to us. But I want to talk a little bit more about these stars and actually how much larger and smaller they are than the sun. So, like I said, the sun is 99% of all the stuff that makes up our solar system, but the most massive stars can be 60 to 20 times larger than our own sun. But they only make up 0.0003% of all stars. So you are 5 times more likely to get dealt a royal flush in a game of Texas Hold'em than you are to pick a star at random and it be an O star. Next are going to be the B stars, which are between 3 and 19 times the mass of the sun. And these are about 0.13% of all stars, so about 1 in every 1,000 stars is a B star. Then next are going to be my 2 favorite is going to be the A stars, which are about 1.5 to 3 times as large, and they make up about 1% of all stars. Then F stars, which are about a little bit larger, 10% larger than the sun, all the way up to 1.6 times the mass of the sun, and these make up 2% of all stars. So everything that I do in my research is only 3% of all the stars, but they are the coolest, I promise. Next, we have G stars, which encompass our sun, and they make up about 5% of all stars. Next are going to be the K dwarfs, and they make up about 11% of all stars, and they're slightly less massive than the sun. And finally, we have the M stars, which make up 75% of all stars. 3/4 of all stars are M dwarfs. Don't listen to him. And they could be as small as 75 times the mass of Jupiter. But how many stars actually are there out there? Well, in the Milky Way, there is between hundreds of billions to a trillion stars. So this image was actually taken by my friend Akshat over there on our recent trip to Apache Point Observatory from his phone camera, which I just thought was really cool. You could actually see the plane of the Milky Way. But there's just about a trillion stars in the Milky Way. So let's try to put that number into perspective. So if we assume that there's around a trillion stars in the Milky Way, and we want to pour one delicious night on Ponce for every star in the galaxy, we would need 12 million oil tanker trucks full of beer. If we line those up end to end, it would wrap around the Earth 4 times. That's a whole lot of beer. All right. But how big actually is the Milky Way? Well, here is an artist's rendition of what we think the Milky Way looks like. This is not an actual image. We would need the world's longest selfie stick to take this picture because we are embedded in the disk of the Milky Way, so it makes it really hard to understand, especially what's going on the far side. But this is our best guess. And we think that the Milky Way is around 100,000 light years across. And we are about halfway out from the center. So we are marked with the yellow star right here. We're about 25 to 30,000 light years from the center of the galaxy. But if somebody was on the other side of the Milky Way and happened to look at Earth, they might see something that looks like that. And a fun fact about the Milky Way is that the Milky Way bar is about 11,500 light years long by 4,500 light years wide and 3,500 light years tall, which means it has an axial ratio of 1 to 0.4 to 0.3. A Milky Way bar has diameter, or has a length of 3.6 inches, is about 1.1 inches wide, and about 0.6 inches tall, which means it has an axial ratio of 1 to 0.3 to 0.2. So the Milky Way bar is almost, or a Milky Way bar is almost a perfect scale model of the Milky Way bar. All right. I thought I had another beer somewhere. Oh, perfect. What? Yeah, well, there's unfortunately no more creed. All right, now we're gonna look, maybe right now, in a galaxy that's not so far away, because I'm gonna talk about the local group of galaxies. So, oh, this is terrible on this screen. We are here, this dot, you'll see, well, you can't see because it's in red. That's where it says Milky Way. And all of these other names, which are probably easier to see than the little dots on the screen, are all the different galaxies that are in our local group. This makes up about 50 galaxies. And the Milky Way, or the local group, spans about 10 million light years across, which means, yet again, somebody was on the opposite side of the local group and looked at the Earth, they'd see something that looked like this. This is called paleoparadoxia, and it is it's one of the only it's the only extinct family of fully aquatic mammals that have ever lived on Earth. But essentially, they were just like fully aquatic hippos. And they were the weirdest thing that I could find that lived 10 million years ago. So yeah, paleoparadoxia. Now you guys know. Okay, so now let's talk about some of the largest objects in our local group. So we have the Small Magellanic Cloud, also known as the SMC. We have the Large Magellanic Cloud, which is the LMC. We have NGC 3109, the Triangulum Galaxy, ourselves, the Milky Way, and Andromeda. And if we want to see how these things compare in size, we can scale them all down to their physical sizes. So we can barely see the SMC over there is about 19,000 light years across. Then we have the LMC, which is about 32,000 light years across. NGC 3109 is about 45,000 light years across. Then the third biggest galaxy in our local group, Triangulum, is about 61,000 light years across. We are about 100,000, like I said before, and Andromeda is about 152,000 light years across. So Andromeda is, we think, is slightly larger than we are in physical extent, but the mass of galaxies is really hard to constrain. So we think that us and Andromeda are actually not that far apart. Andromeda is probably a little bit larger than we are, but they're probably not that dissimilar from each other. But we're actually on a collision course. I just needed any excuse to see this animation because I think it's cool. But here we have the Milky Way galaxy right here, and our timestamp in billions of years over here on the bottom right-hand corner, and then it'll zoom out, and we could see our friends Triangulum and Andromeda. So as this plays out, we will see that Andromeda and the Milky Way, as they get closer, they start to orbit one another slightly, and when they pass there, you can see that the disk, which is actually made up of all the stars and gas, is disrupted. So when we pass by the Andromeda galaxy, some of the stars in our galaxy are going to get thrown off, and they're going to get thrown in all sorts of directions until eventually, about 6 billion years in the future, we will merge into one mega galaxy. But don't worry, I think the sun is going to explode before then, so I don't think we have to worry about getting thrown out of the galaxy. Now, I want to apologize to everybody who is interested in cosmology here because I study stars and know very little of cosmology, so I'm going to skip it. And I'm going to talk about what is actually the extent of our universe. So this is going to be an image of the Hubble Deep Field. So all of these objects that you're going to be seeing, especially a lot of the more extent objects, and the redder objects are going to be really far away galaxies. But last month, oh wait, hold on. So our galaxy, or the observable universe, can only be as large as, or can only extend out to the age of the universe, because light is the speed of light is a constant, nothing can go faster. So we are 13.8 billion our universe is 13.8 billion light years across, well, in any direction, because that's how long light would have to travel since the start of the universe. So, but last month we found this object called MOMZ14, and it was found to be 13.5 billion light years away. So this object formed less than 300 million years after the Big Bang, which is quite remarkable. This is actually the oldest object that we've ever seen. So in this big, giant image, if you zoom into that little tiny area right there and blow it up, you see this fuzzy blob thing. And that's the farthest thing we've ever seen. All right. And to wrap things up, I just want to say that a lot of times you'll hear the old adage, what is there more in the universe? Or what is there more of? Stars in the universe or grains of sand on a beach? Or on all of the beaches on the earth. So if you counted up all of the grains of sand, which you must be one bored SOB to count up all the grains of sand, but there's between 10 to the 18 to 10 to the 19, grains of sand on Earth. And I said before that there's about 10 to the 11 or 10 to the 12, so hundreds of billions to a trillion stars in the Milky Way. And there's about that same number of galaxies in the universe. So that would mean that there's between 10 to the 22 and 10 to the 24 stars in the universe, which is between 1,000 and 1,000,000 Earths worth of sand. So there's most certainly more stars in our universe than there are grains of sand on Earth. You're welcome. When you guys have trivia, you can think back to this wonderful talk. All right. And with that, I'll wrap things up with a video that IBM made quite some years ago, talking about powers of 10. So as it's going to zoom out, and you'll see the squares that are represented with representative of the size that is on the left-hand side, and also in scientific notation on the right-hand side. But with that, I will take questions.
Who's got a question?
God, it must have sucked. Thank you.
Thank you. So how was the image of that mom Z14 captured, and what did it take to get any kind of observations about it?
Yeah.
Your taxpayer money.
You took what I was going to say.
Sorry.
Yeah, about $10 billion. It was taken on the James Webb Space Telescope, which part of the reason that James Webb was launched was to probe back to the early parts of the universe. So James Webb observes in the infrared, so you can peer easier a lot further back in time, because the infrared is not really absorbed by dust, so you can see really far back. And so that was an image that I think was taken end of last year, so maybe October time of last year, and it was just in January that NASA released the statement that confirmed that it was 13.5 billion years or billion light years away. Yeah, crazy.
Who else is out there? Who's got a question? Did you know about this IBM video before you made this presentation, or did you hunt down this IBM video?
Zach actually told me it existed, and then I found it. It is, Zach, do you have any idea how old this video is?
Somebody does.
Yes.
It's about as old as me. No.
Oh, yes.
Now I'm curious.
Oh, God.
Oh, yeah. This was done by the Eames Guard Tech group that created IBM, and it was done about in 78. So these are all artist renditions once you get outside of the Earth. Right.
Yeah.
And once you, I won't spoil it, but the other side of it.
Yeah. Thank you. Called in my brother from the bullpen to answer some questions for me. All right, thank you guys very much for listening to my talk, and yes, this is the right thing.
Yes, it is. Guys, take part. Let's give Colin one more round of applause. If you've been a fan for a long time, or if you just found out about us tonight, you can find where we'll be, wherever we'll be, at the top two QR codes up at the top. And this series, Astronomy on Tap Atlanta, we've been doing it for more than 2 years, exclusively with 3 taverns for free, and we will continue to do this exclusively with 3 taverns for free. But I will tell you that the majority of excellent talks that you have seen, including tonight, are done by astronomy PhD students or astronomy PhD candidates. They're graduate students